The third section is define estimation. In this section, there are two lessons. Define estimation. What is the basic process for coming up with an estimate? How do we know if it's a good process? And the second lesson gives us an overview of reasonable practices and a roadmap for the techniques we will cover. To set that up, what I typically do in my in person training is this next exercise. I ask participants to estimate three things. In the first estimate, I allow them 15 seconds to come up with their estimate. The second estimate, we estimate exactly the same thing, but I give them 90 seconds to do the estimate. Finally, in the third estimate, they are again estimating the same thing, but I give them about 5 minutes and they create an estimate as a group. There are some rules for the group estimate, as you can see here. They need to create a new estimate, not just an averaging of the previous estimates or a voting of the previous estimates. What we see almost every time is that in their first 15-second individual estimate, we have a very large balanced relative error. If you don't remember BRE, check out the describe estimation error lesson. This really large error is driven mostly by wild guessing, which, not surprising, is inaccurate. Many people don't even understand what they're estimating, but they had to put the number down, so they did. In the second 90-second individual estimate, we see a smaller but still large BRE, not nearly as bad as the first estimate. That is, the BRE percentage has dropped, but we still have many estimates that are wildly inaccurate, off by a factor of 2 or more. We do see, though, that a few are doing pretty well. By the time we get into a third, 5-minute group estimate, we see that the BRE has really collapsed, and it is rare that any group is wildly inaccurate. And almost all estimates are within a factor of 2 of the real number. Most are within a factor of 1.3 or 1.4. They're doing a much better job. What we discover here are some interesting things. First, when we do this exercise, we can gain some insight into our estimation behaviors. Because that first estimate, that wildly large BRA one, what we tend to see is that people are just guessing on very limited information. They don't know. This is very common in the real world. We often make estimates off the cuff without the complete picture. Then in the second estimate, they modify their technique. They're able to say, you know what? There's so many people in the room. I kind of know what we're estimating. Now I'll come up with a ratio of the number of items of interest per person and then do the math. They count and they compute on more known things rather than pure guesses. When they get into the group, they keep basically the same count and compute process, but they're able to calibrate their number based upon getting more information. The number of items the people in the group have as a way to improve the ratio. By calibrating the ratio, the group estimate tends to do a lot better. We're going to see that progression as we look at how we do better estimation. When we do estimation, we see that there's two aspects. There is a science of estimation and there's an art of estimation. Many people focus only on the science of estimation. Not a bad idea, since the science is actually pretty good. Unfortunately, it mostly deals with theoretical numbers. That is, we present the science to you, we have to present the theory. And the theory is always a prettier picture than the reality. Also, the science is complex enough that we must apply it with tools. We're almost always going to use some sort of tool to implement the scientific side of estimation. And these tools are not plug and play. You must calibrate and tailor the tools to your specific environment. When you take the time and expense to calibrate the tools, then you can get the accuracy you want with the appropriate precision. That is, you can get within plus or minus 10% down to plus or minus 5% in the mid range of the cone. But a lot of us aren't going to use these tools. They're expensive and they're difficult to calibrate. But what most of us need to do is shift focus from the science of estimation to the art of estimation. Can we get estimates that are reasonably close most of the time? The art of estimation is practical help on everyday projects. To go from wildly inaccurate to reasonably close is a huge win. The art of estimation can get us there, and we can still use tools if desired. Maybe use much simpler tools like spreadsheets and historical records. Our goal with the art side isn't to be that costly plus or minus 10%, but we be within plus or minus 25% most of the time. Because if you're close to the real number most of the time, you're able to make good business decisions. And that's what good estimation should do. It should help you make good business decisions. But how does a typical estimate happen? How do people typically estimate? Well, this graphic here shows how a typical estimation process works. The inputs that people put into the estimate are roughly similar, but every individual has a slightly different take, slightly different list of what they consider important when they're thinking of their estimate. This variation makes it very hard to repeat it, very hard to improve it. The input goes into an internal calibration and conversion process. I call this internal process the process. And the process looks at the inputs and goes, 8 months. An output. The process is opaque, unrepeatable, and difficult to impossible to improve methodologically. Now I have my output, say 8 months. I have no ability to prove that number correct because there's no visibility to how the inputs got converted. The estimate consumer can just attack the output they don't like. I said 8 months? They were hoping for 6 months? I could just go, again. Okay, 6 months. Why not? Now, this is how most estimates happen, and it's not very good. In fact, I don't think it's even totally fair to call it an estimation process because, again, the inputs vary by individual, the conversion to outputs is opaque, and the output is not defendable. Classic software engineer author Fred Brooks addressed this when he said it is very difficult to make a vigorous, plausible, and job risking defense of an estimate that you've basically made up. You're not going to go and defend that. And what's fascinating here is that he said this in 1975. Why haven't we figured this out by now? Why can't we solve this? Because it's not a science problem, it's an art problem. It's about how we need common understanding between the people doing the estimation and the people consuming the estimates. Yeah, there's some technique issues here, but it's often more a people problem than a technique problem. We would have solved it if it was just a technique problem. Fred's comment was true in 1975, and it's still true today. Our preferred estimation approach looks more like this. We have the core, a standard estimation procedure. This is where we're going to bring a little bit of that science, a little bit of those techniques that we need, techniques that are observable and repeatable. We feed this standard estimation procedure primarily with technical scope. How big is it? How much is there? We always want to start our estimates with size. We happen to have a schedule constraint. We need to know the priorities. What should we build first? What is the value order? We desire to build the most value possible given the third primary input, the constraints, the iron triangle relationship. Do we have a fixed schedule? Do we have a fixed scope? We need to know what is fixed so we can estimate the flexible one. To make that estimate procedure work really, really well, we need to calibrate it with some historical data. Historical data is the thing that turns poor or even moderate estimation practices into good practices. The better your historical data for your group and your team, the better your calibration. And then the better your estimates are going to be. We put all that into our procedure with these techniques and generate our outcomes, our estimates. The primary estimate is our estimated effort. Converting size into effort using a calibration is the primary goal of the procedure. From effort, we can use formulas in the procedure to generate a cost estimate, a schedule estimate, and if the schedule is fixed and not estimated, a feature or value estimate. Those are the estimates the procedures should generate. We'll probably also have some assumptions, things that we hold to be true to make this estimate work. We'll talk more about assumptions later, but just a warning here. We want to make sure that the things that we assume to be true have a high chance of being true. That is, we don't want assumptions here like the earth is flat and so this number will work, when really we don't believe that the earth is flat. The primary input is size, the primary output is effort. And it's probably important to note here, just to be careful, to separate out estimation from scheduling in the overall planning. There is the estimate, where our input of size is calibrated to effort, and then the nominal schedule is derived. Remember, a nominal calendar time is the amount of time we are equal likely to go over as to go under. Not great odds. I wouldn't promise that to anyone else. A nominal schedule also isn't worried about who's currently available or not available because it's a planned schedule. The nominal schedule is just saying, hey, Given how big this is and our historical ability, we can do this in around this much time. Now, a planned schedule can always take longer, so I often take a nominal schedule as a more optimistic point. However, estimating a nominal schedule can be fast. I argue that a reasonable estimate should take 15 minutes or less. Estimating a nominal schedule is different than creating a planned schedule. If my estimate nominal schedule is reasonable, I'm then willing to put the effort into creating a planned schedule. If I'm too far off in my estimate, if the nominal is too big, like my estimate says it's 8 months and we're hoping for 4, I'm not going to try to shove 8 months worth of work into 4. It's not close enough. I want to attempt this only if it's close. And once I start thinking about a planned schedule, I need to think about availability. Who's available and when are they available and all that kind of stuff. The big point here is while the estimate schedule could take 15 minutes or less, a planned schedule can take days or weeks to figure out. Estimation becomes a tool to say, is it worth investing the time to do that detailed scheduling? If it's close, great. Let's do the detailed planning. If it's not close, let's not bother with a detailed plan yet. If forced to come up with a detailed plan, my estimate says is foolish, I might as well quickly make stuff up, as it'll have just as much validity as making tons of crazy assumptions to try to put 8 months worth of work into 4. At the end of the project, what needs to be true to say we hit our estimate? Well, we need to have good estimation techniques that correctly calibrate size and effort. We also need to have a rational target that doesn't drive us into unrealistic assumptions to make the number work. The target needs to be based on reasonable expectations. We need to keep the expectations and the reality of the work in sync. Once we get going, we need to have acceptable project control. That is, we need to make sure the scope doesn't creep wildly, that we don't lose all resources, and so on. Hitting the estimate is more than just coming up with a good estimate. We have to have an interplay of multiple factors to hit the numbers. Good estimation will give us the ability to control and make decisions about these things going forward. Good estimation gives us control because we progressively elaborate the estimate. That is, we're constantly examining and refining the estimate. Your work effort has an overall timeline. Yes, you'll have to come up with some initial estimates. Those initial estimates help us decide whether it's worth investing any time and energy on this work. If so, we'll do some of the work and hopefully reduce uncertainty. We will then be ready for another estimate that we can use for a baseline plan. Now, the baseline plan says, okay, here, given the refined scope, given this amount of resource, here's what our estimate is. If that estimate is in line with the target, we will spend the effort to build a planned schedule. We will measure ourselves against this plan, even though the world may change. Our continued estimates throughout the work effort will alert us to deviations from the plan early enough that we can make corrective actions. We use estimates to look at the work itself to tell us how we're doing. Poor estimation practices sort of assumes that we can look once at the beginning and know the future. Unfortunately, real software projects are complex. We need to be able to look at them repeatedly to make good decisions so that we can maintain that project control. We will approach doing estimation in two main ways, one called top down and one called bottom up. Most people are familiar with the bottom up path. That is, we look at individual items and then we combine them to come up with an overall nominal effort that we can then derive a nominal schedule. This approach is very common. In fact, it's probably the most common way I see estimates being created when I go out to clients. They're only doing bottom up estimates. But the question they face in early estimates is, do they have the knowledge about the parts or are they guessing what the parts even are? Usually, early in projects, we don't know most of the parts. We guess or assume them. The parts are not known. They're just guesses. And now we're estimating guesses upon guesses. And that doesn't turn out very well. So early on, we need to do a top-down estimate. We need to look at estimates from the top and say, okay, given this thing that I know, I don't know well all its parts yet, but I know the thing at the thing level. What's an effort estimate for this thing? Top down is what we'll see very early on, and then we'll get to know the parts by doing the work of the project. Well, at that point, we'll switch to bottom up. There are four notes I think you can walk away with from this lesson. First is that estimation is an art and a science. I'm not going to downplay the science too much. The science is important, but most of us can get all the improvement we need out of the art side. Art is where there's huge gains to be made in the world of estimation, and we can capture that art and a little bit of that science in the estimation procedure. That's the thing that we can look at and then improve on and refine as we learn more and more about how you create estimates in your own organization. And then when we come up and do an estimate, the nominal cost or nominal schedule is different than actually doing the planned schedule. Estimation comes up with a nominal. Reality could take longer. Heck, we have infinity on the right side of the probability distribution. Finally, we'll start early in the work effort with top down estimate. This is probably different than what you do today. Most of us need to make the transition away from early bottom up estimates.